Welcome to the Professor's DuBois channel. This is Professor Corey. In this video is a mini lecture based on our second lecture covering material from Chapter 7. We're going to begin this lecture with a recap of what we've learned so far. First, realize how we can label our periodic table as S block, P block, D block, and F block. You should know the corresponding L quantum number for each, and with this, you can determine the total number of arrangements of the orbital in question from m sub L. The orbital fill order can be realized using the periodic table as well, and you read it similar to how you would read a book, where you would start at the upper left and read the first line. At the end of the line, you start at the next line down on the left and read toward the right. We can see the fill order written in black just below the periodic table. In red, we have shown the full SPDF notation for the element zirconium, along with the noble gas notation written in fill order and N order. The very bottom shows noble gas orbital box notation for the element zirconium. You should at this time be able to write these configurations for every element on the periodic table. There are some exceptions to the fill order described in the previous slide. The ones you're responsible for are listed, and all of these differ from what would be expected by promoting an electron from the s orbital to the d orbital. The correct noble gas SPDF notation for chromium is shown. Be able to recognize the exceptions as they make excellent test questions. Before we write electron configurations for ions, we should review ions. Ions have a charge shown in the upper right of the element symbol. The charge can be positive or negative. A negative ion is called an anion, and it has gained electrons. The electron configuration for anions is completed by simply adding the electrons, the extra ones, in fill order. You will notice that nonmetals typically form anions that give them the same electron configuration as the closest noble gas. Cations are positively charged ions. This happens when an atom loses electrons. There are some rules listed on this slide that may make more sense with an example. Worth mentioning is that a good approach to writing the electron configuration of a cation is to first start with the electron configuration of the neutral atom. From here, rearrange the configuration to increasing n order, then remove the necessary electrons to form the ion. So, for this example, we will start with the electron configuration of the neutral atom of magnesium. The ion has lost 2 electrons, and these are taken from the highest n, which is 3. Again, you will notice that many metals will lose electrons in a quantity that results in a noble gas configuration. The neutral tin atom has electrons in both s and p orbitals at the highest n. We will begin by removing electrons from the highest L, which is L equals 1, or the p orbital. The transition metals will often form a 2+ ion. This is because the highest N is an s orbital that holds 2 electrons. The exceptions do not have 2 electrons in the s orbital, only 1. Use the same rules as before, but do not promote any electrons after forming the ion. The exception is for the neutral atom only. Chromium is one of the exceptions. There are 1 electron in the 4s orbital and 5 electrons in the 3d orbital for the neutral atom. The chromium 3+ ion results from removing 1 electron from 4s and 2 electrons from the 3d orbital. Isoelectronic species have the same electron configuration. We have seen many examples of this in this lecture, as the ions often result in a noble gas notation. As an exercise, write the electron configurations for the fluoride, oxide, nitride, sodium, and magnesium ions. These should all have the same configuration as the noble gas neon if they're done correctly. Additional practice will include electron configurations for the 5 exceptions mentioned. Thanks for watching. Please give the video a thumbs up and subscribe if you would like to see more videos on the Professor's DuBois channel.